Hi everybody. Today we're going to start talking about what happens when objects experience a change in momentum. We've talked about momentum and what it is, so hopefully we realize that as an object changes its motion, it also would change its momentum. And we want to look at how that happens. So our objectives for this lesson are to be able to define a term we call impulse, which is essentially the change in momentum of an object. We want to be able to relate impulse to an object's change in motion and therefore its change in momentum. And finally, we want to be able to solve problems involving momentum and impulse. So does the momentum of an object change? Well, of course it can. We are going to look at objects that do not change their mass. So as a result, if they don't change their mass, and momentum depends only on mass and velocity, the only way that we're going to see a change in momentum of an object is if an object changes its velocity or, in most instances, its speed. If you remember, in order to experience a change in velocity or speed, the object must accelerate. And if an object accelerates, there must be a net force causing that acceleration. So that sort of tells us what makes sense to us. In order to speed something up, slow something down, or change its direction, something that is acceleration, we have to apply a force to an object in order for that to happen. So let's look how we can relate that force now, just not to acceleration, but to the actual change in motion of the object and perhaps the change in momentum. Let's go back to Newton's second law. Remember, if we want an acceleration to occur, we have to apply a net force. Or if we apply a net force, we have an acceleration that occurs for our object. And remember, an acceleration is a change in motion, and that's what we're looking at when we are trying to look at a change in momentum. So let's do some substitution and see if we can come up with something that'll help us not just relate the force and the acceleration, but the force and now its subsequent change in momentum because of that acceleration. So let's rewrite this guy a little bit first. And we'll say now the F equals m, and we'll replace acceleration with its definition of the change in velocity, Vf minus Vi, divided by the time interval over which that velocity change occurs. We'll do some algebra and move that time over to the other side by multiplying each side by time. And now we get force times the time exerted, or essentially a time over which the change occurs, ends up being equal to the mass of the object multiplied by its change in velocity. If we distribute that mass through on the right-hand side of the equation, you will see we'll get mass times velocity final minus mass times velocity initial. And if you look at mass times velocity, we have momentum. So we would get the force exerted, multiply the time over which it is exerted, is equal to the final momentum of the object minus the initial momentum of the object, which essentially is the change in momentum of the object. And this guy right here is how we define impulse. Impulse is simply the change in momentum of the object that is caused by a force being exerted on the object over a period of time. That time is the period over which the change in velocity occurs, and therefore the change in momentum occurs. Impulse is, in your book, I do not believe it has a variable. Some people represent it with an uppercase J. We're in class just going to say impulse. So impulse is equal to the change in momentum. Now you may ask, what about the units? If I say that impulse, the force times the time, is equal to the change in momentum, well, you're probably going to say, well, the units of momentum that you know are kilograms times meters per second. And if you look over here, you're going to say, well, if I take force in newtons multiplied by a time in seconds, you're probably going to ask yourself, are they really the same thing? Because you have to think, if you want to change momentum, you should be changing momentum with the units of momentum, not with some other type of units. So let's look at remembering what a Newton is. Remember, Newton we got through F equals ma, and it's really a kilogram times a meter per second squared. And if we multiply that Newton by a second for our time, this 1 second cancels out one of those seconds, and we actually do end up with the same units of measure on each side to say that our impulse can be equal to our change in momentum. So whichever type of units you prefer to use, you can use Newton times a second, you can use kilogram meters per second. They are equivalent. It's just that they're derived through different methods. But you want to realize that they are equivalent. So as a result, even if you say Newton times seconds, or if you say kilogram meter per seconds, you're talking about the impulse or the change in momentum. This impulse equals the change in momentum is what we call the impulse momentum theorem. And if you look at it, you can see that we have quite a lot of things that are defined here. This is impulse is equal to the change in momentum. That change in momentum is equal to the mass times the change in velocity of the object. Or if you look at it, you can say it's equal to the final momentum minus the initial momentum. You will find as we go through in solving problems, it depends on what you know as how you're going to approach trying to find out impulse. Can you find out the impulse by just finding out the change in momentum? Yes. Can you find the change in momentum by finding out the impulse? Yes. The one thing that you want to remember that as we do problems in class, we are only going to approach problems where the force is constantly applied, meaning the force value is constant over the time interval over which it is applied, or it has to be an average force. An average force meaning it may change over the time period from initial to final, but we're going to look at an average value to get an overall average change, which would mean we would see an average change in momentum and therefore an average change in velocity. The values may fluctuate within the time period, but we're just looking at the beginning to the end. Now, when you look at the force that can cause a change in momentum of an object, many different forces can cause an object to slow down or to speed up. It depends on the amount of time over which the force is exerted. So if you look for trying to change the momentum of an object, you can do it in various different ways. It depends. The longer you exert the force, the smaller the force has to be in order to create the same change in momentum, say, of a larger force over a shorter period of time. Think about, for example, you're driving in your car and you're approaching a red light. If you are driving at 20 miles per hour, regardless, you want to get to 0 miles per hour. So you want to change your momentum a fixed amount. If you use a little bit of forethought and start trying to change your momentum or slow down way back from the stoplight, you only have to press your brakes a little bit, exert a small force, but over a longer period of time as you're moving towards the stoplight. If you wait until the last second, right as you get up to the stoplight and you go, uh-oh, I have to now change my momentum to 0 in order to stop, you're going to have to exert a lot larger force over a very small period of time, or essentially slam on your brakes in order to cause that same change in momentum. So you want to realize that when you want to change the momentum of an object, you can accelerate it in different ways, to slow it down or to speed it up. The size of the force that you can exert is going to dictate how long you have to exert the force in order to change the momentum of the object. And let's just look at a quick example, make sure that all our units and everything work out. So here we have a 1,400 kilogram car. It's moving westward with a velocity of 15 meters per second. It hits a utility pole, and it comes to rest in about 0.3 seconds. It wants to find the force exerted on the car during the collision. All right, so let's look at what we know. We know the mass of the car is equal to 1,400 kilograms. Okay, we know that the initial velocity of the car is 15 meters per second. All right, and to make my life easy, I'm going to say that the westward direction is positive, so that I can take that 15 meters per second and put a positive number in front of it. I'm going to say that my final velocity is 0, because it told me it was brought to rest. And I know the time over which that force is exerted by the car interacting with the utility pole is equal to 0.3 seconds. And it's asking me essentially for the force that the pole exerted on the car. So if I look at what I could usually do, here's something where I could go into my F equals ma, find out the force, find out the acceleration, all that type of stuff. But I could also figure out the change in momentum of the car, because I know that the impulse is equal to the change in momentum, which is equal to the mass of the object multiplied by the change in velocity. So we'll do a little bit of rearranging. My force is equal to my mass times my change in velocity over my time. Looks very much like F equals ma. And let me just do some substituting in here. So my mass is 1,400 kilograms. My change in velocity is my Vf minus my Vi, which is going to give me a negative 15 meters per second, right? Because I'm changing my velocity from a greater to a lesser, divided by my total amount of time over which that force occurs. So if I plug in all my values, I get my force is equal to minus 70,000. And again, kilogram meters per second divided by another second gives me kilograms times a meter divided by a second squared, which is coincidentally a Newton. So the force that's exerted on the object or on the car by the pole to create that change of momentum is essentially 70,000 newtons. The negative sign indicates the direction, which would be to the right, which completely makes sense. I'm traveling westward to the left. I am slowing down, so my acceleration has to be to the right. The force that causes it has to be to the right, has to be in the opposite direction of motion in order to be a slowing force. So you can see that this is just another way of explaining the motion of an object. Based on what we know or maybe what we don't know, sometimes it's more convenient to use change in momentum versus some of our kinematic equations where some of that information, where we had to know a lot more variables, we may not need to know as many in this case.